Hello, this is Dr. Heidelberg, and our presentation today is PLC and communication in mechatronics. We'll follow the reference textbook by W. Bolton, Mechatronics. We are in Module 11, chapters 21 and 22. The topics that we'll cover include the PLC, basic structure, ladder programming, relays, timers and counters, data handling, and programming example. We'll also talk about communication networks, protocols, OSI models, serial, parallel, and wireless. The PLC acts like a conductor in an automation orchestra. It's responsible for the synchronization of all the automation devices which are acting together in a manufacturing process. We see here an example that shows the PLC at the center point. It communicates with the peripheral equipment through the communication channel of Ethernet. It also communicates at the lower hierarchical level with motion controllers of automation devices such as XYZ stages or robots. Each has several axes. Each one is operated by a servo amplifier driving a motor and an actuator and feeding back signals through the I/O channel into the PLC. The PLC is programmed by a programmer, operator, maintenance person, assembler, or tester via a laptop or teach patent. There's also a human-machine interface to emergency machine off that shuts off the system in emergency. And the PLC also connects to the higher level hierarchical control loops, which may reach to a cloud or an Internet of Things devices. We'll see that the PLC applications are expanding from 2011 to 2006, almost doubled in various applications like food and beverage, machine tool, material handling, packaging. Virtually any automation process is using them, and you see that the level over here is in revenues in millions of dollars. There are also training available. They last like a few days on PLC, specifically in different PLCs or combinations such as Siemens, very popular, Allen Bradley, very popular. You see that the course is around $2,000. And there are also opportunities, as we saw today on Indeed, for PLC programmers. You see that the salary range goes from 50 to 90. Various places in the country. It's not a difficult subject to learn, and it could be an interesting option to folks who would like to advance their careers. The definition of a PLC by NEMA, National Electrical Manufacturing Association, is that it is a digitally operating electronic apparatus which uses programmable memory for internal storage of instructions and using functions such as logic, sequencing, timing, counting, arithmetic to control through digital and analog I/O modules a process. We see here the block diagram. We have the operator that communicates with the PLC in the controller and downloads the program. The PLC has input modules, output modules. Inputs are fed with sensor. Outputs are being actuated by the signals of the output, and the actuators run the process, and the process provides through sensor feedback to the PLC. We see how it is connected over here. We see the power supply unit. We see a CPU with a memory. We see also the input and the output. We see a point for the relays that drive the actuators. Also communication through RS-422 or 232 or an Ethernet communication and also high-speed communication over here through the communication bus. Over here is an example of a PLC high-level hardware example. We see again the power supply and the PLC and the input and output, and over here the memory. Each slot has its memory definition over here, so the programmer knows exactly what location the program is existing. And then the real mirror image of the hardware diagram is shown over here. Power supply and PLC and various input and output. And you see over here that the cables also are very nicely arranged with marks that identify it for easy process in case of failure. The way the PLC works in one scan cycle, the PLC reads the input signals, it executes the program with the input signals, it diagnoses whether there is an issue or goes to operate a call, an interrupt call. It also uploads the output and repeats the process over and over and over again. Here we see a PLC scan cycle, for example. It's a Siemens 1511 CPU with 15 millisecond cycle time. And we see over here the scale of 15 milliseconds. And then this is on the lower pink blocks. And then there are communication with the peripheral equipment. And you see that it takes like 0.15 of a millisecond time. And then where there is an interrupt, for example, high priority motion control operation, such as an actuator, then the process stops, the PLC runs the motion program and then goes back and continues the cycle. Over here we see an example of a PLC ladder logic diagram. We have here the left side where you can imagine that this has the power, and over here is the sink. And in order to get the output, then the input has to be closed. For example, if that is a switch, it has to be closed. And then if it is closed, there is a connection which connects the power to the ground, and then it operates output A. When output A is done, then and input 1 is also closed here, and then if input 3 is closed here, then output B will be on, and then when we come over here, then either output 4 or output 5 could close the channel. This is an OR gate, this is an AND gate, and that will operate the output C. And then this is the end of the ladder program. Some PLC manufacturers could accept a ladder diagram as a programming, and it's very common sense-based logic. We see over here an example of timers and internal relays that could add into the ladder diagram program. Here we have an input 1, and then there is an output 1, and then output 1 closes this switch, and then the timer starts to operate. Once the timer starts to operate, when the time has reached its destination, then output 2 is closed. And we see over here a different designation of a timer, the same thing over here on the first rung. These are called rung. It calls ladder because it looks like a ladder. And then output 1, and this is a timer. You get in here, this timer is the time that it has to run before the output comes in and actuate the output 2. And then we have an internal relay. What's internal relay? Here we have a parallel link of input 1 and 2. When either one of them is on, internal relay 1 is on. then if output 3 is on and 4 is on in an AND gate, then internal relay 2 is on, and then if either 1 or 2 internal relays is on, then the output is going to be on, and that's the end of the program. We have also latches. What's a latch? When we have an input, this shows an input that has to be closed, and this input is normally closed, but it has to be open to disconnect the output. So if this is not disconnected and input is closed, the switch is closed, output 1 is on, and when output 1 is on, then this link is on, and it's going to be on independent what will happen to input 2, because when this is on now, there is a connection to the output over here. And we have also a counter possibility to add to the ladder diagram. We start with input 1, the switch closed. The counter resets itself. Then input 2 is closed. The counter starts counting, and that it counts until the number of cycles is completed, like a number of conveyor pulses for each box that has to be packaged. And then when the counter reaches its counted number, it closes, and the output 1 is on. Here we see an example of a jump. We have, for example, a case where we want to set an alarm if a temperature sensor shows temperature greater than 80. So we put the 80 in this memory D. We put the sensor data into this memory S. And if the sensor data is greater than the set data 80, then we start the alarm. And then the alarm over here is going to be closed, and it's going to be on as long as this condition is fulfilled. And then if the sensor data is less, we see over here less or equal to the designated data, which is 70, then the internal relay is on, and then this is off, and the alarm shuts off. And we see over here a jump routine where we run the program, and then when we hit the jump, if this condition is on, 1 is on. If 1 is closed, we jump, we go right in here. And if it is not on, then we continue with the program with these rungs to the end. There are PLC instruction codes by various PLC suppliers. We see over here Mitsubishi, Amran, Siemens, and the mnemonics is LD, for example, is load operand into the result register. Start the rung with open contacts. LDI is load negative operand, AND is a Boolean AND, any is Boolean AND with a negative operand, OR is OR, and so on and so forth. So these are the instructions which are found at the manuals of the PLC vendors. We see over here that the notations of a load is 2 bars, which have to be closed in order to conduct. We see over here that the inverse, in other words, this is normally closed, and it will open upon operation of the signal. This is the output. This is conditional jump. This is end jump. This is a shift register. And then we have here the AND logic. We have the OR logic, 2 in parallel. We have the NAND logic, meaning that the output is off if both of them are open. If either one is closed, then the output is going to be on. And then we have also a NOR gate. And these are the mnemonics for load inverse. As we saw earlier, different vendors may have the different mnemonics. Here's an example of a PLC application. We have over here a motor, and we have a switch to start the motor, switch A. We have over here light. When the motor is on, we like the light to be on, and this is the switch for the light. And we have a buzzer that if there is an obstacle being detected, then the switch is on and the buzzer will be on. So here's the flow chart. We start, we define the switches. The input switch is A, input switch 2 is B, LED switch is L, buzzers is BU. And then what we have here, if switch A is A, and we define it over here, and then we ask if there is an obstacle. If there is an obstacle, then switch B, which is detect an obstacle, is on, and then we put the output buzzer on, and if not, then the motor is started and the LED is on. And we see here different ways of writing the program. Here is the more popular ladder diagram. So if A is closed and then the buzzer is not on, motor is turned on. And then if C is turned on, the light switch is on, then we don't have a buzzer over here, then the light diode is turned on. And then if the buzzer is shut down, we're detecting detecting an obstacle, and the motor is set off by opening these two switches, then the buzzer will be on. And then there is another Boolean expressions of writing this by saying that the motor is on when A and not B is on, and the light is on when C and not B is on, and the buzzer is on when B and not A and C are on. And over here is a different mnemonics for another type of writing this program. And we see over here the pretty recent EtherCAT protocol and configuration, which is 16 kilohertz servo cycle update, which is extremely fast. It could, for example, drive a position loop of like 10 axes in less than half a second or several kilohertz, which is extremely fast. You see here are the motion controller that we saw earlier on the block diagram is connected through the EtherCAT through the data bus to various clients or slaves, amplifiers, and access controller. Then it is communicated through the Ethernet to PLC. It's a lower rate channel of communication. And then it could also receive data from sensors, various measurement devices. And then PLC is connected to the host computer, which is further connected to a cloud through the internet. There are several ways that the network of communication topologies can be arranged. This is a designation of a data bus, which is used for networks which are more than 100 meters. Here's a star where you have a central computer and all the devices, such as in the corporation, are connected to it. The disadvantage is that if it is, if this is damaged or has a failure, then it may affect all of them. This is a hierarchical control, as we saw earlier, typically used for more than 100 meters. This is a ring configuration, and this is a mesh configuration where each one of these circles is a node with a device, a microprocessor, or an actuator, and then the communication links are the lines. The protocols are defined by the OSI, Open System Interconnect model, that shows us 7 layers in order to provide safe and reliable communication. The top layer is the application, where we write the application program interface, the program that has to be transmitted. And then there is a next layer below it. This is the highest level, which is the presentation, taking this format and do a character decoding and data compressing. And then there is a session layer for the data, where it manages the connection between the source and the destination. And then we have another layer, layer 4, which is the transport, such as the TCP or UDP, that set the segmentation. It may take a very long message and chop it into pieces and do some multiplexing. Most of this is done by software. And then we have the hardware layers of the media, such as a packet network. It takes the segment, the TCP as shown over here, and adds to it the IP address. It does the addressing and the routing. And then we have a data link, which is further being addressed as a connection between the reliable connection within the physical link, which is the first link or the lower link, which is transmitting just bits. And that is the hard wire and connector of the system. This shows us an example of a TCP header, where we have the source port with 16 bits, and then we have the destination port, and all these bits go one after the other, and they're transmitted serially through the various communication network, all the way from the source to the receiving. And it has also a sequence number of the sequence, which has to be assembled at the end, acknowledgement number to assure that the message so far was received, and then it has a data offset to let the receiver know how far is the data, how many bits away the data is from the starting point. And then there's a checksum to make sure that the data received is correct one. And then there's the data. The data transmission has 3 main elements in the protocol: syntax, which sets the data format and the coding; semantics, which takes care of synchronization and control; and timing, which is the data rate and the sequence of transmission. The data access is done by various means, such as token passing, where a token is being circulated as a bit pattern. And then when a device would like to transmit the message, it attaches it to the end of the message, and then it is removed by the next transmission. There's a slot passing, which circulates, and then a device may deposit the message inside the slot. And the CASMA CD, carrier sense multiple access, collision detection, it waits actually until a message is no longer existing on a local area network before it sends the message, and it therefore eliminates collision. The protocols which are commonly used in industry is MAP, Manufacturing Automation Protocol, developed by GM for its plant; TOP, which was a technical office protocol for Boeing Computer Services; Novell Network; Allen Bradley Data Highway; Mitsubishi MelSecNet. Then we have different other communication protocol for RS-232, commonly used for serial communication, R2C bus, which is 2 wires labeled as SDA data, SCL clock, very common in microprocessor, small equipment. Then we have CAN bus, control area network by Bosch for car, and this is passing low number of bits between the various components on a network. Then we have USB universal serial bus, which monitor printers, modem, and PC device. FireWire, which is serial bus by Apple. GPIB, general purpose instrument bus, developed by HP, connecting computers with instrument. VME bus by Motorola, used for connecting microprocessor instrumentations. And this is a backplane bus, which connects CPU, memory, graphics, and disk control cards in a computer on a backplane. The wireless protocol standards, there are several of them. A satellite, which is used to connect phone to antennas, which are far, about 10 to 15 miles, and they are called GSM. We're more familiar with the 3G, 4G, and 5G and Edge. We have the Wi-Fi, which is the wireless area network, and this is the internet access to devices which are within the range of 66 feet from the access point. And then we have RF protocols like the Zigbee, and that is used for low power RF radio transmission, which is embedded within electronic devices, which is range for 30 meters. Then we have RFID, which is a frequency of radio to identify objects, and it is installed on active readers. Bluetooth is transferring information between near devices like sound and with telephones and data bytes with handheld computers. And then there is near-field communication, which uses electromagnetic inductions between 2 loop antennas within near field to each other, and it's getting more and more popular. The local area network is the LAN, the small area which is used by bus, star, and rig topology. The wide area network is for global, national, and international networks. Broadband, which is used on these protocols, is conducting several signals which are modulated simultaneously over several radio frequencies, and sometimes it's only one signal at a time, which is called a baseband. This completes our presentation, and we'll continue with examples of Metatronic systems in our next lecture. Thank you.